Right.
So we do find B of right
Section, page 29. Let me just plug my laptop in so I don't run out of battery like I usually do at the end. So 5, the last one we'll do for today is another wave question. So I do hope that these Newton, wave and electricity questions are starting to get easier. Silence means you can vote. I can always vote yes. Alright. Is there a spare chair? There's no plastic chair in the back? No. I just don't want the cable to pull out. Equilibrium. Okay. I think this one is recording now. Okay. First part, what does coherent mean? Yeah. Coherent is same frequency. Okay, what is constructive interference? It sounds like constructive interference, yes. What's that mean? Constructive interference, what is it?
When crest of the wave meets the crest of another wave.
Yeah, in other words...
As waves are added.
Yeah, when two waves combine so that the new wave is bigger in amplitude. So you have one wave plus another wave and the result is a bigger wave.
Then we can addition of waves, as you said in the...
Addition of waves is fine, yeah, but positive addition. When you combine... Yeah, you don't care for constructive interference about frequency. Constructive interference is about making the amplitude bigger, and then destructive will be making the amplitude smaller, and then completely destructive will be cancelling the waves. Okay. At a certain point on the screen, the waves interfere destructively. What is the phase difference between the waves at this point? Express this in both degrees and radians. Okay, so I'll just sketch the graph by hand. But basically the question is asking you what happens when two waves cancel each other. So for example, in red is the first wave, and then in blue is the second wave that cancels it. So the second wave must look like that to cancel it. Now, I want you to look at this and imagine that the blue and the red wave are the same, except you just move them a little bit to get them into place. So my question is, if you were to copy this red wave and move it, how much would you need to move it to make it into the blue wave? Well, you have to move it to here. Yeah, half the wavelength. So in math class, you know one wave or one cycle, we can call it 360 degrees. They want the answer in degrees and radians. So instead of saying half the wavelength, what do we say? Yeah, the answer is 180, or in radians? Pi. Okay, that's part 3. Part 4. Lambda is 628 nanometers. Double slit, 9.8 from the screen. Minus 9. And okay, so we have D is 0.9. The fringes are 2.5 millimeters. And they want the slit separation. Yes, that's what they said. So we use, we need S, and our formula is lambda equals x d over s, isn't it? Yeah, it's this. So S equals x d over lambda. Now, do we know the lambda? Oh, we do. Oh, so we know everything. Alright. So we have x times d divided by lambda. What's wrong, Joshua? Oh, thank you. I have it upside down. Are you 100% sure that's what I'm going to do? I can easily check just here. It is xs over d. Thank you. Okay, so retyping that in. S is then lambda d over x. Okay. Lambda times 0.9 divided by 2.5 divided by 10 to the... I got 2.26. Yeah. 0.2 of a millimeter. Alright, that's A part 4 done. So now on to B. Vibrating tuning fork of frequency 256 is held over a long vertical tube of water. The water level is gradually lowered until the air in the tube above the water vibrates at the first position of resonance. What type of longitudinal wave is formed in the air column at this point in time? So the standing wave. What you have is, there's your tube, and you have your wave inside of it. The frequency is 256 Hertz, and it's 1/4 of the wavelength inside of the tube. Right. Explain how this wave is formed. I don't know what you want. Definition of a standing wave? Yeah, I guess so. I'm curious. I need to hear the answer in the marking scheme. What did they go for there soon? Run through that again one more time from the top.
Interference
Yep.
of the incident wave and the reflected wave. The incident wave from the tuning fork
Yep.
and the reflected wave is from the bottom of the
That's a terrible explanation. Right, so what they want to know is, how does this wave form? So I guess
You hit the fork.
you hit the fork, yeah, bounces, comes back. I just feel like they're missing an awful lot in that. But anyway, whatever they want. So the wave comes in, it hits the bottom of the tube and then reflects out. But the result of the reflection is such that the two waves going in and out stand together as one wave. Okay. I think the example that you usually see is if you have a rope against the wall, and if you flick it a little bit, you can see the wave moving down and then bouncing and moving back. That's not happening here. What's happening is when you flick it, the wave that's formed, when it bounces back, it's exactly the same as what was sent into it. So then it, it doesn't move forward and backwards then. So I suppose we could say the wave going in and the wave coming out, they interfere constructively. Okay, I'll go with the sound wave that enters combines with the reflected wave that leaves in such a way that causes a standing wave to be produced. That's almost as bad as the other one. Okay. Draw a diagram to represent the amplitude of the particle displacement along the wave in the air column and label the nodes and the antinodes. Well, I've actually done that already here, part 3. Just tell me where's the node and where's the antinode. So, which one is the... Let me draw that again, that's terrible. Okay, so we have our pipe, and I'll try my best here to draw this. I should really draw it like this. And what's happening is it's vibrating back and forth as a standing wave, so some of the time it's there and some of the time it's here. This one here is then the node, and then here, antinode. So this is the part that's vibrating a lot, and then this one's not moving. And then this is 1/4 of the wavelength. Draw a diagram to represent the amplitude of particle displacement along the wave in the air column and label the node and the antinode. I don't know. There's the particles there, and then haters are there. I don't know how good of a diagram they want, but critically I have the node, the antinode, and the wavelength labeled. So I feel like it'll be 1 mark for this, 1 mark for this, and 1 mark for the correct wave shape. Okay, if the length is 0.33, what's the velocity of sound? Okay, so that's now where we use the formula with the 4 in it. The length will be 4 times 0.33, the wavelength, which is 1.32, and V equals F lambda, which will equal 256 times 1.32, so that is 338 meters per second. Okay, so that's part B done, so now on to part C. The source of light, wavelength, angle for the first spectrum, the light source is replaced by purple light having red. Okay. I'll try and draw that. Can I scroll down to the last part? Yes. So what you have here is you have your light, and then you have your grate, and then you have your screen. A source of light of wavelength 550 nanometers. The angle for the first is 30 degrees. N equals 1, this angle is 30 degrees, and it's 550 nanometers. The light source is then replaced by purple light, which has a different wavelength, and so on, so on. What is the spacing of the lines in the grating? So for the first part, I have enough information to get the D. I know the formula is N lambda equals D sine theta. So D equals N lambda over sine theta, which here would be 1 times 550 times 10 to the minus 9 over sine 30, which is I got 1.1 times 10 to the minus 6, 1.1 micrometers. Okay, that's part 1. Yes, it is. Part 2 now is what is the angular separation of the first order red and violet rays after they've passed through the grating. So what they're saying is, now you come along with your purple light, and the purple light will make a bigger or smaller angle. Well, let's think now. The purple light has a bigger wavelength, and bigger wavelength means bigger angle. So what's going to happen is here we can find this angle, and what they want to know is what is the difference between the two angles. They want to know what is the angular separation, the angle difference. Okay? So we use our formula again.
Right, purple.
Yeah, I don't have purple, I just drew it with blue.
Smaller.
It doesn't have... Oh, sorry, smaller. What's the 700 then?
700.
The light source is then replaced by purple light having red wavelength 700. Ah, sorry, no, we're not even using the same light anymore. We have two different lights. So I need to draw it again. Okay. So the first light is red, yes? And what's that wavelength? 700. And then the second one is violet, and what's that wavelength? 400. So that's going to be smaller. Okay, so we know the formula n lambda equals d sine theta. So sine theta equals n lambda over d, but in both cases we're just looking at the first one. So you have sine theta equals lambda over d. So for the red, you have theta equals sine inverse for the red, 700 nano over d, which is 1.1 micro. And then for the violet, it's sine inverse, same deal nearly, 400. Okay, so let's get the two angles here. First one, sine inverse, fraction 700 times 10 to the power of minus 9 over 1.1 times 10 to the power of minus 6. I got 39.52 degrees, and then for the other one I will get 21.32 degrees. So the difference between the two is 18.2 degrees, is the angle difference between the two at the first order, where n is 1. Can you just double check that for me please soon?
Yes.
It's correct? Fantastic.